Start streaming. So as of now, I should be streaming on Discord, or screen sharing. Term is screen sharing on Discord and live streaming on YouTube. And I'm just gonna double check. Yep, I am live streaming, so I'm gonna close that window. All right, and I got 6 seconds to spare. Woohoo! Woohoo! Yes. All right, so let's go ahead and get started. So what we're going to do today is the application of what we have learned so far. So you can look at this kind of as a reinforcement of the concept that we have learned. You also might want to identify key moments of the lecture to basically say, okay, so this is when TAC starts to talk about how to access a parameter, or this is when he talks about how to use a pointer, how to dereference a parameter that is a pointer, or this is where he specifies a return value, and so on and so forth. So just kind of having a your own catalog of those specific topics and the moments within the lecture can be helpful. Now, I cannot guarantee that that's going to be like super duper helpful, but I can almost say for certain that some people could have benefit from doing that throughout the semester. Well, it's not too late to start. We still got what, 2 weeks or so, so it's not too late to start. This is still a good time to get started with that. All right, so as I have typed in the course server, what we're going to do today is to write a program to basically do the same thing as string copy in C. So let's go ahead, and I'm just looking for my text window that is of the right size. Let me see if I still have that maximized. Yep, I still have that. Very good. All right, so the first thing we want to do is to basically look it up and find out, okay, what is string copy? This is one of those things that should have been introduced, like many other things, in CISP360. Okay, so in CISP360, your professor should have introduced the concept of a string, which is basically just an array of characters, and and what string copy is about. Okay, it is just to copy a string. Now, as much as I understand that string and copy is a safer version of string copy, we're just going to be focusing on string copy today, simply because it is easier and quicker to implement. So there you go. Are there any questions about string copy? Do you guys want me to explain what it does, and or are you guys ready to move on? I'm not hearing any. Oh, okay, there you go. Yeah, here comes Omir. All right, so I'm not going to briefly explain it. Instead, I'll plagiarize from the man page. All right, so description. The string copy function copies the string pointed to by src source, which is the second parameter, including the terminating node character, no byte, to the buffer pointed to by dest, which is our first parameter. The strings may not overlap, and the destination string dest must be large enough to receive the copy. Beware of buffer overrun, see bugs. Okay, so that basically is what string copy does. Is source is pointing to an array of characters, and it is technically a string, not an array of characters, because it is null terminated. I think that is the main difference when people talk about an array of characters, which is length delimited, because the size of an array is based on how many bytes you have allocated to the array. But when you talk about a string, the length of a string, it depends on when you find the null terminator. On the other hand, we have dest, which is also an array. And in C and C++, arrays and pointers are basically interchangeable. Anything that is a pointer can be seen as an array. So dest is an array of characters, and the job of string copy is to copy the null terminated string pointed to by source to the destination, which is also an array of characters. So is that does that suffice? This question is for Omer. Okay, very good. It also has a return value. Okay, it doesn't have a void return. It's not a void function. It returns a char pointer. So we also want to look up and say, okay, what does it return? The string copy and string end copy functions return a pointer to the destination string dest. In other words, whatever you pass as dest is whatever you return, and you can see how a particular implementation of string end copy is simply returning dest as the return value. So we are not using string end copy. We're using just string copy, because this way, the program is a little bit easier to describe within the time of this lecture. All right. So before we move on, do we have any other questions about string copy? All right. So Bernard has a question, probably. All right, so the question is, are we going to convert the simple implementation right here into assembly? Well, this one is not what we want to do. This one is a string end copy. So what we're going to do is to perform a string copy, which is actually easier compared to this. So does that answer your question, Bernard? All right, excellent. All right, so what we'll do is we are going to start with a C implementation first. Double check, make sure the C implementation is working properly, and then we'll move on to talk about the assembly language implementation. So let's go ahead and start with, I'll just call it string copy.c. And we'll go ahead and pound include stdint.h, standard integer.h. So this way we can refer to integer types that are width specific. And then we'll say int8 underscore t star, which is a pointer, my string copy. Because if I use string copy, it can potentially cause a problem, because the compiler will, the linker will automatically try to link with the C standard library, which includes string copy. So I don't want to run into that potential problem. And a char is basically just int8 underscore t. That's basically what a char really boils down to. It is actually a signed 8-bit integer. Don't ask me why it is signed. Okay, it doesn't seem to make sense to me that it has to be signed, but it is. So this is our destination, and then we have int8 underscore t star src. And if you want to preserve the const, that's fine. We'll just add a const here. So what that const is trying to say is, even though source can be changed within the subroutine, what it points to cannot change. So the const is applying to the int8 underscore t, which is the content that is pointed to by source. But source as a parameter actually can be changed within the function itself. Okay, there's nothing preventing us from changing source. We just cannot change what source is pointing to. All right, so I'm going to give you a sane implementation first, and then we'll ignore that, and then we'll implement an insane implementation. All right, because I do want to kind of get into recursion, because I have been itching to get into recursion for a while now. So tonight is my chance, to actually get into recursion. So here we go. All right, so do you guys want the most intuitive way to do this, or do you guys want the a slightly trickier way to do this? I would just put it that way. So which one do you want? Do you want the tricky? Okay. All right. So the people have spoken. All right. So this is tricky, but it's still using iteration. Okay, when I say tricky, in this particular scenario, it is not that tricky. It's just a little bit tricky. Intuitive. All right, I'll give you both. How about that? I'll give you both. So I'll give you the intuitive first, and then we'll give you the tricky, and then I'll give you the insane. Just like a Tesla. You guys do know that Tesla, or at least some Teslas, have three modes, right? In terms of the response to the accelerator. Yeah. So we'll emulate those three settings. So we'll go for intuitive first. So intuitive is kind of like this. We'll use an int I as an index, and then we'll use a for loop which says I is initialized to 0, and then we'll say let's see, what would we do here? Actually, do while loop makes more sense. So we'll do a do. Okay, I is initialized to 0. We'll do a do while loop here. Okay. Let me say. Let me think about this. Let me think about this. Yeah, okay, that would work. I mean, there are so many different ways to do this. I'm just thinking about which way is going to make more sense. So return dest. Okay, so that part we know, and then we have to say, what are we going to do in the loop? So what we're going to do in the loop is simply to say dest I gets source I. Okay, remember both of those are seen as arrays, and I is an index into that array. And then everybody's going to say, but when are you going to increment I? I'm going to increment I here. So the way I'm going to increment I is to say while source I plus plus. Ding. Okay, that's it. This is the intuitive version. Yes. All right. So let's kind of check out what this is doing, right? So what this is doing is it is first performing the assignment, and you guys are thinking, don't you want to check whether we are at the end of the array before we actually copy something? No, we don't, okay? Because we're guaranteed to have to copy at least one character because it has to copy the null terminator itself. So we are guaranteed that we have to perform at least one copy, so might as well do it first. And then what we do here is we are looking at the current character that's in source, which is where we're copying from, and we are using post increment, which means I is incremented only after this entire expression is evaluated. So it's a post increment, which also means the actual index being used is before it is incremented. So we are basically saying if source I, source bracket I, is non-zero, then we want to go back and perform another iteration of this loop. But increment anyway, after the evaluation of this Boolean expression. So that's going to copy every single character into from source into destination. So we are going to test this, right? We're going to test and see whether it works or not. So here's main. There we go. And then in main we're going to have an array. So we're going to have an array. We'll call this, where should we, we'll just call it buffer. Okay, I'm just not particularly inventive tonight. We'll just call it buffer. And then we'll say my string copy buffer, which is our destination, and then we're going to use a literal string as the source. Okay, there's nothing wrong with using a literal string as long as it does not have any more than 255 characters. And someone's going to say, but Tech, the buffer has 256 characters. So why did I say 255 characters when I specified the length of the string? I'll have you guys to try to answer that question. Exactly, because there's a null terminator taking up the last byte of the array. So there we go. And since we want to test to make sure that it's returning the right value, so we can use put s, as a way to test. Put string is really just an easy way to print a string without using printf or cout. And then we have a return 0, but I think we need to use standard IO now. Because put string is it's defined in standard input output as a header file. All right, so let's give it a try. Okay, gcc-o temp string copy, temp, whoops, temp string copy.c, and then we'll go ahead and run it, which is temp string copy. All right, so it works fine. Okay. And for those of you who are not really convinced, you can use a debugger. Go in and just kind of double check to make sure the buffer does have everything, which is this is a test exclamation point and then a no character also in there. All right, so this program works so far, and this is the intuitive version. So let's go for the not so intuitive version, which I'm calling tricky. All right, so we'll get rid of this stuff here, and then we'll use the other version. So the other version looks like this. It's using a single while loop, and the while loop, the condition of the while loop is going to get a little bit interesting. Okay, so it's going to say start dereference dest gets dereference source, and we'll even use plus plus here as well as plus plus here. And oh, I need to save destination first, so we'll go ahead and use in8_t old destination is destination, and then return old destination. All right, so this is the way we're going to do it. All right, so the question in the text channel is, what if the string is 0, 0, 0, 0? This is the classic question about it's about the differentiation between the character 0 versus the ASCII code 0. So those two things are different. One is specifying what the computer should print out on the screen, and that's the character of 0. The ASCII code of 0 is the null character itself. So the string 0, 0, 0, 0, 0, 0, 0 is just going to print as 0, 0, 0, 0. Not a problem. I'll leave that experiment up to you, but I'm just going to tell you, if you change, this is a test, to 4 zeros, it will just print 4 zeros. There's nothing special about that case. So I'm going to just kind of put it that way. So now let's take a look at this code here and go like, whoa, what is this? What is this doing here? Well, okay, so before we go any further, some of you may not remember the priority of operators. So I'm going to add some additional parentheses just to show what is taking precedence over what. There we go. So we have post increment of dest being used as a pointer, and then we have a dereference here. In other words, this is the location that is being changed, and this is intentional as a single equal because this is intended as an assignment operation. It is not a comparison operation. And on the other side, we have kind of the same deal. Your source is a pointer. It is post incremented and then dereferenced. So we are basically, once again, we're just copying whatever source is pointing to whatever destination is pointing to, but then we do a post increment of both of those pointers. So when does it stop then? Well, it stops when this expression here is 0, is null. And this thing here, so what I have highlighted on the screen, that is an expression. This is one of the things that differentiates C or anything that is C based from other programming languages. As far as I know, C, Java, JavaScript, anything that's based on C are languages that are the only languages that will support an assignment as an expression, because what the value of an assignment expression is the value being copied. So this is why I can basically just combine a whole bunch of stuff into one single expression. Now, if you ask me, is this the best programming style? No, it's not. But it is a good way to illustrate what you can do in C and C++. So do we have any questions about this program, especially line 7? You can ask that question because I can hear some people screaming in their head, which is, where's the body of that loop? Destination is not a pointer to the array. Destination is a pointer to a character, which is also considered the same as an array. Where's the body of the loop? The body of the loop is right here. So let me move my cursor to the body of the loop. Right there. That semicolon here, that's the body. So there you go. Which is equivalent to, okay, fine. I understand some of you really do not like to look at the semicolon as a body of a loop. Is that better? Yes, that's the whole purpose, because I want to implement my string copy to conform to exactly the same specification as what is described in the man page. So in other words, this program should be doing exactly the same thing as the previous program. Okay, so we got a few more people asking questions. All right, cool. I like this. Okay, I like you guys looking at this code and start to ask questions, because that reflects your processing, right? You're actually paying attention. All right, so although it would be pointless, could you also have a for loop without braces? Yes, you can. Indeed, you can. All right. So we got Gannon typing, and I'm gonna wait. I mean, we don't have to hurry too much. So at this point, you can kind of look at the beginning of this class up to here, which is like 20 minutes, to be a review of topics in CISP 360. All right. Okay, so we have Tam typing. I'm gonna wait a little bit here. All right, so the assignment operator is used instead of the comparison operator. Not instead of. It's not instead of. There was no intention whatsoever to use the comparison operator here. So does it mean when it reaches the null terminator, the loop ends? Yes. Well, that was kind of the intention, because an assignment expression returns the value that is being copied. So that means when the null character itself is being copied, then the assignment expression itself becomes 0. And in the context of a Boolean place, a 0 means false. And in the case of a false, a while loop will get out of the loop. So that's why it's going to work. Well, that's why I think it's going to work. It remains to be seen, to whether this works or not. All right, so we can see that Gannon is still typing. So we are gonna. All right, there we go. Why can we no return dest and erase line 6 to get the same outcome? Because destination is being changed. I mean, you have to use one more variable regardless, because either I make a copy of destination here and then use the copy of destination in the loop, or I save the old value of destination into a different variable, local variable, and then return that old variable here. Either way, I need one additional variable, so I just chose to do it this way. It's not the only way to do it. All right. So are we good so far? Are we ready to test the code and see whether it works or not? All right. Well, from the absence of questions, I'm going to test this code. Okay, so let's go ahead and compile first, and then we'll go ahead and run this code like that. And it works just the same. All right, cool. All right, so remember what I said earlier? This is the tricky one, and I'm going to give you the insane one, and that's the one that we're going to translate into assembly language. And then some people are going to scream and go like, why would you use the insane version to translate into assembly language? Because I want to focus on calling subroutines, and I want to make this recursive intentionally to illustrate a few very important points. Okay, so the insane version, not insane, well, I did call it insane, so let's call it the insane version. It is recursive. So with recursion, if you guys have not taken CISP430, anytime you deal with recursion, the first thing you think is, what is the simplest case when I do not need to perform a recursive call? Okay, so that's always going to be the first thing in your mind is, under what condition do I not need to call the subroutine again? The subroutine that you're in calling itself. When do we stop that? Okay, so that is usually the first thing that you need to determine first. So we are going to say dest gets source. Okay, which is an assignment expression. This is kind of unique to C and C++, and anything that is derived from C and C++ is assignment is an operator, so it can form an expression that can go any place where you expect a value, which is kind of cool, but it's also very confusing because sometimes when people actually intend to use double equal and they use a single equal, the program is not going to work anymore. Except in some cases, it might continue to work for a little bit and then it dies. So so that's kind of the thing where you go like, okay, so it's tricky. C can be very tricky. All right, so now we're going to use a question mark, which turns this into a ternary expression. In other words, we are looking at the assignment expression as a condition. If it is true, which means we just copied a non-zero byte, that's the time when we call my string copy again. So we will call my string copy again, and we just have to move destination by 1 byte, and then move source also by 1 byte, like that. And now we have a problem because this recursive call is going to return dest plus 1 and not dest, right? So it's going to mess up my return value. So in order to compensate for that, I just have to subtract 1 from the return value of the recursive call of my string copy, like that. And on the other hand, if the byte being copied is a null terminator already, then I go like, okay, we are done. We just return destination then. So this is the recursive version of implementing string copy using a single ternary expression as the return value. There's no control structure per se because you don't see any if then else here. All right, so I'm gonna let you guys, kind of process this a little bit before we translate it into assembly language. Well, I bet you a lot of people did not even know that you can use assignment as an expression, and it just gives you a value. It just gives you the value of whatever is being copied, which is handy in some cases, but it can also lead to a lot of problems, in the wrong hands. I'll just put it that way. Using C, C++ as a first introductory programming language is analogous of running a wood shop and you have a bunch of apprentices and you're giving your students a circular saw which is no more than just a motor with a blade welded onto the axle of the motor, and there's no switch. You just tell your students, just hold on to the motor really, really, firmly while I plug it in. It might give you a jolt, okay, when it starts. Just hold on to it really, really strongly. And there's no blade guard whatsoever. That is C++. Yeah, it builds character at the expense of a few fingers or limbs. Yes, I would totally agree with Omer's, assessment. Yeah, before C and C++, before universities started to use C and C++ as the introductory programming language, they used to use Pascal. And Pascal has pointers, but it is a very tight sandbox. There are only so many things you can do with pointers. So it's not nearly as dangerous as C. Alrighty, so let's check, make sure this program works, and then we'll go ahead and implement this in assembly language. So there we go. We have to compile first, and then we run the code, and it works exactly the same way as before. So now we feel confident enough that we can translate this code into assembly language. All right, so let's go ahead to do just that. Oh, I can copy that first. So we'll cp string copy.c to string copy.ttpasm. And now we'll just work with string copy.ttpasm like that. And obviously every single line has a problem because it is not in TTPASM syntax. But that's okay, we know this trick already. Replace the beginning of each line with // so we comment out everything. So there we go. Okay, so that's pretty easy to do. And we start with the usual stuff. Start with a no op. That has to do with a bug in Logisim. And then jmpi to main. So this way we can preserve the definition order of the functions in the C code. All right, so we'll get to, well, we'll get main first. Okay, so main is here. And main is, oops, just an entry point. Okay, so the entry point of the function needs to have the same name as the name of the function itself. And now we have a local variable. So now the question is, where do we put local variables? So this is a question for you guys to kind of think about, where are we going to put our local variables? Eric is right. Everything is on the stack. Everything is on the stack. And local variables are on the stack as well. All right, cool. So let me initialize the stack pointer first. Okay, so I'm going to initialize the stack pointer right here. It's not necessary because when you reset the processor, all registers are reset to 0 anyway. But I'm just putting it here just to emphasize it is important to make sure that your stack is empty before you get to main. All right, so how do we do this allocation? Well, as it turns out, there are I cannot do 256 bytes as a buffer. Why not? Why can't I use 256 bytes for my buffer when I'm using when I'm trying to translate this code into TTPSM? It's not the entire stack. That's the entire RAM. And it has to share that entire RAM space between code and the stack. So we definitely do not have that much space on the stack. So what I'll do is I'm going to give you, it corrupts the entire program. So what I'm going to do now is to define a buffer length. Okay, so it's always good to define a buffer length. And this is how we define a const in TTPASM. It is almost exactly the same as defining a label because it is a definition of a label. It's just that you tell it exactly what the value of the label is supposed to be. So now, we are basically telling the assembler every time you see buffer length, it's the same thing as 32 as an integer value. All right, so this is a different way to use a label definition. Is you tell the assembler exactly what value you want the label to be defined as. All right, so with this, what we're going to do is to say, okay, so I guess we're going to have to reserve 32 bytes on the stack at this point. So the way we're going to do this is to subtract 32 from the stack pointer, which is register D. So most people would just go like, oh, it would be nice if we can do this, except we cannot, right? We talked about this already, why we cannot have this kind of instruction. It is not a limitation of the syntax of TTPASM. The syntax is almost an afterthought. Okay, it is just a way for us to specify an opcode in the same way in the form of a mnemonic. The reason why we cannot have something like this has to do with the pathways within the processor. There's no way to grab the constant of 32, which is going to occupy a location in RAM, and feed it into the ALU as one of the inputs. There's just no path to do that. So that is why this is not going to work. So what we need to do instead is to say, okay, let's put 32 or buffer length. That's the whole reason that we define buffer length, is to make it symbolic. So now we can use register A. So you have to put a constant value into a register first before you can use it in an arithmetic operation. All right, so what this is going to do is to basically say, okay, we are going to save the locations from, let's see, let me do the counting here, 220, my math is bad, 223 all the way to 255. No, I take it back. It's 200 and 224. Thank you, Philip. From location 224 all the way to location 255, those locations are now reserved, okay, because I just moved the bookmark not by 1 byte this time. I just moved it by 32 bytes, okay. So in essence, I have just told the gremlins, okay, remember those gremlins that we talked about? I just told the gremlins, you cannot touch these 32 bytes now because they are now above or at where the stack pointer is pointing to, because that's the agreement between me and the gremlin. It's like, okay, everything below that and above the last line of code, you guys can play with that, but everything that is above where the stack pointer points to or at where the stack pointer points to, that's out of bound for you guys. So this is protecting that area already. All right, so we have just saved those locations, okay? So the next question is, how do we specify a literal string like this, right? This is a test. So for the assembly language program, I am going to try to save myself some trouble, because otherwise it's going to take a while to translate this is a byte unless I write a program to crank out the byte code. So we'll go ahead and use a very strange label. So I'm going to use underscore lit string 1, okay, underscore, and having these kind of strange prefix and suffix is intentional. So we're going to put this, we can put it anywhere. So this is a label, and what we're going to do, I'm just going to truncate this string to this, okay? So now what we need to do is to look up the ASCII code of THIS, okay? So we're going to say byte, and then we have to look up the ASCII code of T. So let me go ahead and look it up, man ASCII. Alrighty. Alright, so let's find the decimal version of uppercase T. Some of you probably have it memorized. You would think that having taught your classes for so long, I would have that memorized too. But nope, I do not have it memorized. It's 84. Okay, so 84 is uppercase T, and 104 is lowercase h. Okay, so let me try to remember that. 84 and 104. Okay. So 84, this is, oops, there we go. So 84, this is our uppercase T. 104, that's our lowercase h. Once we find h, I is easy because I is right after, right, in terms of alphabetical order. Lowercase s is going to be too far away, unless you want me to count it. I'm not going to do that, so I'll just go ahead and man again. This time to look up. Oops. Do it one more time. Man ASCII. There we go. All right, so we want to look up. Oh, I just typed the wrong key on the keyboard. One last time. All right, so let's look up lowercase s this time. So lowercase s is 115 in decimal. All right, there we go. No, that cannot be, right? 115 is lowercase I. Did I mess up my math? Or did I mess up the way I looked at the table? I must have messed up. Oh, okay. There we go. Thank you. All right, and don't forget the null terminator, right? So now we have the string, the literal string, this defined, in assembly language. All right. All right, so now we have to push the arguments on the stack, right? Because we have to push the literal string, which is pushing the address of lit string 1 on the stack. And then we push buffer because we have to, when we have more than one arguments, we push the last argument first. So the last argument ends up with the higher address, and then the first argument ends up with the lowest address when you have multiple arguments. All right, so let's do that. So we're going to LDIA with underscore lit string. Whoops. There we go. Decrement D, so we reserve 1 byte, stda. So this is for pushing this on the string on the stack. So you can see that we are not really pushing the characters on the stack. We're pushing the address of where where we're going to find the first character on the stack. And then we're going to push buffer on the stack. Now that gets a little tricky because where is the buffer at this point? The buffer is no longer where the stack pointer is pointing to. Instead, the buffer is now 1 byte past where the stack pointer is pointing to. So this is kind of important. So so now we have let's see. So I'm going to define an offset here. Okay, so we'll say buffer is 0 byte from where the stack pointer points to normally. Okay, so this is basically saying your buffer is 0 bytes from where the stack pointer points to, but now it is not. It's not because we just pushed one extra thing on the stack. So what we need to do is to do LDI, and we're going to introduce another trick about what you can do with an immediate value. Wherever you can specify an I. This is a trick you can use. So we will specify buffer 1 plus. So this is it's basically the same thing as buffer plus 1, but it is using a postfix notation. So TTP-ASM does allow you to use expressions to evaluate so you can have addition, subtraction, multiplication, and division. The only thing you have to pay attention to is it doesn't deal with infix notation. It only deals with postfix notation. So in postfix notation, you specify the value first, and then you specify what you are going to do with the values. So in this case, we specify the two values. One is buffer, which is literally just 0. The other value is 1, and then we specify a plus. So when the parser of the assembler encounters the plus, it's going to say, okay, in order for me to perform addition, I need two things. So what are the two things that are now pushed on the stack? Okay, now this stack has nothing to do with the stack in the processor. This is the value stack. So the value stack has buffer n, which is a 0 and a 1 on it, and then the operation of plus is going to take these two things and add them up, and then it will return the value to replace the two things that it took from the stack. In essence, this is doing the same thing as buffer plus 1. Okay, so this is a postfix notation to perform that. And then we're going to decrement D again, stda, and now we need to push the return address. So let me specify what we are pushing this time. So we are pushing buffer on the stack this time, and then we need to push the return address on the stack. So to push the return address on the stack, let me show you yet another trick you can do with postfix notation here. So this time we're going to say .6 plus. And I'll tell you exactly what it does, in just a moment. So let me finish doing this first, and then I'll tell you what this is actually doing. My string copy. There we go. And we'll also put in a comment here and say this is where my string copy should return to. Okay, there we go. All right. So now the big question is, what is .6 plus? Now, the one thing we know is it is a postfix expression. In other words, it's adding the dot and the 6 together, and whatever that sum is going to be the value that is going to be loaded into register A. So the actual question in this case is, what is dot representing? So the dot is simply representing the address of the LDI opcode itself. So the LDI instruction here has an opcode, and that opcode is occupying a certain location in RAM. That location is known to the assembler, and we can refer to that location as a dot. In other words, the value that we're loading into register A here is 6 bytes after the address of the LDI opcode itself. Okay, so does everybody understand that statement? We are loading an integer or an address that is 6 bytes after the opcode of the LDI instruction on line 24 into register A. So is that okay so far? That's the first thing we need to understand. Okay, so I can see it's all silence, which means you guys are processing. All right. So let's go ahead and try some experiments, okay? Because nothing illustrates this better than just running through a few, I would say, simple experiments. All right. So let's go back to. Oh, I meant to go to my drive. There we go. I'm just looking at the time, making sure that we have sufficient time to finish all the topics, and I think we'll be fine. All right, so go to source, get rid of this entire program first. All right. All right, so what we're going to do here is really just to test, okay, the suffix notation and whatnot. So we're going to define a label, let's say L1, and we're going to say L1 is 2, 3 plus 4, 2, 3 plus 4 times 5 minus. Okay, so what do you think is going to be the actual value of L1 in this case? We already know that this is a postfix notation, which means we specify the value, and then we have an operator to consume the specified value or values to perform the operation. It's 21. Well, let's see. I don't know for sure. I have to do the calculation myself. So the 2 plus 3 is done first. Okay, so 2, 3 plus, it will give us the 5, and then it's combined with times 4, and then minus 5 is the last operation. So let me just kind of put in extra parentheses here, just so that we understand the nesting of the operation. So that would be 25. No, it's going to be 15. All right, so let me bump up the font size here so we can see better. There we go. All right, so what is happening here is 2, 3 plus is going to give us 5, and then that 5 is going to be a value. So 5 and 4 will be available for the multiplication. That's why when we perform the multiplication, it's going to be multiplying 5 and 4. That will give us 20. So then we'll have 20 and 5 as the values being available, and then we perform the subtraction. So it's equivalent to 20 minus 5, which should give us 15. Okay, so Eric is correct. Han Hughes should be correct as well. So how do we know? I mean, tech, you can say this all day long, but how do we know this is actually the value? 15 is the correct value. So you basically go to the SimTab sheet, and we can see how L1 is defined on line 0 because it's 0 oriented, and an RPN is essentially the value after we evaluate the postfix notation, and it is indeed 15. This is in base 10, so it is indeed 15. So you guys got it right, okay? And before anyone says, but this is a really, really obscure way to have expressions, well, the only reason why we think this is a weird way and this is the correct way is because we have been poisoned by infix notation ever since we got to school. Okay, depending on where you grew up, it can be as early as 3 years old. So we have been learning infix notation all this time and not realizing that it is not really the best way to represent expressions. That's the best way that I can say it, because it needs a lot of parentheses. If you use postfix notation, there's no need to use parentheses at all. And That's one of the appeals of postfix notation is it doesn't need parentheses, and there's no such thing as operator priority, because it bypasses all of those concepts. By using the infix notation, we have to introduce operator priority, parentheses, and all kinds of weird stuff to just to specify the order of operation. Postfix notation doesn't have any problem like that. All right, so that's kind of cool. And then we're going to have a no op instruction here, and then we have an LDI instruction here, and we're going to say LDIA with dot plus, oh, whatever, right? Dot plus 6, fine. And then we'll specify a bunch of no op instructions, and I'm going to let you guys determine the address of which no op is going to be loaded into register A on line 3. That's going to be the question. So the no op of which line, the address of which no op on which line is going to be loaded into register A when we execute the LDI instruction on line 3. That's the question. I wish I could hum the Jeopardy tune as well as I think I should be doing it, but since I cannot, I'm not going to do it. But it's kind of like Jeopardy. All right, so let's figure this out, right? Okay, so we'll go ahead and figure this out. So we'll figure this out, and then we'll go to the Assemble tab just to make sure, right? So this is dot. Okay, so on line 3 we're gonna have dot and dot 1 plus as the addresses because it's gonna take up 2 bytes. So that means on line 4 we're gonna have dot 2 plus. Okay, this no op is corresponding to what we see as dot 2 plus from the perspective of line 3. And then this is going to be dot 3 plus, and I'm not going to type anymore. This is dot 4 plus, dot 5 plus, and this is going to be dot 6 plus. So my guess is this is going to be dot 6 plus. So most of you or some of you guessed line 9 because you forgot that LDI took 2 bytes. LDI takes only 1 byte for the opcode itself, but the constant is going to take up 1 additional byte. So that's why line 3 is going to take up 2 bytes. In other words, this is how you can count it as well. 0, 1 is line 3, 2 is line 4, 3 is line 5, 6, 7, I cannot even count. Okay, 0, 1, 2, 3, 4, 5, and 6. So I am going to guess the address that's going to be loaded into register A would correspond to the address of the no op on line 8 here. So you guys might think, oh, we need to compile this code and run it in the processor so that we can figure out whether that is right or not. Well, we don't even have to go that far because all we need to do is to go to the Assemble tab right here, and we just need to look up what is on line 3, and you can see on line 3, oh, this is not good. Because I did not use infix notation. Okay, I take it back. I did not use suffix notation. I used infix notation. Man, that is embarrassing. Because all this time I'm talking about suffix notation, how cool it is, and here I go by mistake using infix notation. Darn it. All right, let's try that again. Cool, this time it works better. So there you go. So LDIA dot 6 plus, which is the same thing as dot plus 6. So we are loading 07 into register A. So 07 is corresponding to this byte here, and it is indeed the no op on line 8. So it's the address of the no op on line 8 that we are loading into register A here. All right, so what else are we going to do? Well, next we're going to do we're going to use the same kind of instruction that we have seen before, right? Which is decrement D and then LD, let's see, STDA, decrement D, STDA, and then we need to jump to a certain location. I don't have a label defined for it yet, so I'm going to use JMP to 0. So let's do the counting again, okay? This is 0, 1, 2, 3, 4, 5, 6. So this time, because JMPI also uses up 2 bytes, so that's why this time the value we are loading into register A is corresponding to the address of the no op on line 7. So let's double check, make sure, right? So the no op on line 7 has an address of 07, and here's our 07 as the immediate constant value that we're going to load into register A. So is that okay? I mean, does everybody kind of get the idea of what .6 plus is doing? And this time we don't need to use a label to define the return point for the subroutine because .6 plus is taking care of that. Are we good so far? Or at least generally speaking, we are kind of getting the idea? All right, excellent. All right, so as I talk about this, you should be taking notes, okay? At least jotting down, the approximate time when I start to talk about a specific topic. So this way, it's easier for you guys to go back and go like, oh, okay, I just need to revisit that specific topic a little bit, and you can locate that time on the YouTube recording just like that. All right, so Bernard said the address +6 is the address of the opcode +6. Yes. But since the opcode itself takes up 2 bytes in the case of LDI, so that's why on line 24 it is accounting for offset 0 to offset 1 already. This is offset 2, this is offset 3, this is offset 4 and 5. So this indeed is the right place because when the function is done, this is where we're supposed to get back to. All right, so when we get back here, we're back to main, which is the caller, and the caller is responsible to deallocate the arguments. And how many bytes of arguments do we have still sitting on the stack at this point? Remember, the subroutine will make use of and deallocate the return address. So even if the subroutine or the function is deallocating the return address, how many more bytes are still being in use at this point on the stack, not counting buffer itself? The 2 arguments, right? Each argument is taking up 1 byte, so we need to deallocate the 2 arguments. So increment D is going to be deallocating the first argument, which is buffer, and increment D again is going to deallocate the address of string, the literal string. So that's why we need 2 increment D here in order to deallocate the 2 arguments. The subroutine cannot deallocate arguments because the subroutine actually does not know how many arguments has been passed. So that's kind of the deal here. So after this, we are almost done here. Okay, so technically speaking, if you halt here, the program is kind of done, except your stack is not going to be balanced. Because what else is being on the stack right now? In other words, the gremlins cannot go back and touch everything on the stack. What is being protected from the gremlins at this point? You kind of have to look at what we first. Oh, Mark has an answer. Go ahead. Nope, the return address was consumed by the function itself. So the return address was consumed by the function, and then the caller, which is main, is also taking care of the other 2 bytes, which are the arguments. So what else? Yes, Christopher is right. The buffer is still on the stack. So even though some people may argue, but you don't have to do anything at this point because there's nothing happening past this point. Yes, in a way, but at the same time, it is proper to make sure that your stack is balanced. So by the time you get to the end of main, we should have the stack pointer going all the way back to 0. So that's why we are going to use these 2 instructions on line 31 and line 32 to deallocate the buffer itself, which are 32 bytes on the stack. All right, so that's main. Now we need to look at things from the perspective of my string copy. So we'll take care of the easy stuff first. Okay, the easiest thing is to define the label as the entry point, string my string copy is the entry point. And then the other really easy thing to do is to specify the return statement. In other words, we're just going to specify the code to return to the caller, okay, but not so much the return value. So we'll go ahead and use the usual LD BD increment D and then JMP B. Okay, so that's for returning to the caller. So now in between, we got some complicated stuff to express. So in the previous lab quote unquote quiz, you kind of learned how to get to your arguments, right? But it's a very clumsy way to get to the arguments, because now you have to remember how far are we, how far is that parameter away from where the stack pointer is pointing to. And you kind of have to do all the mental math and keep track of everything. You might need a piece of paper and draw, the relative positions of everything on the stack. So that's probably a good way to get started. Okay, so we want to kind of figure out what is on the stack at the entry point of the subroutine. So we know source is pushed first, so it has the highest address. Okay, so I'm going to emphasize this has the highest address. Next thing, we have the destination, which is our first parameter, and then we have our return address, and the stack pointer is pointing to the return address at the entry point of the subroutine. That is the handshake. This is the agreement between the caller and the function, is basically what we are seeing here from line 8 to line 10. The stack pointer is always pointing to the return address, and then the arguments or the parameters are always immediately following the return address. And the ordering of the parameter is the first parameter always has the lowest address amongst all the parameters, and then the last parameter always has the highest address amongst all the parameters. That's the agreement between the caller and the callee. Well, part of the agreement, because there are some additional agreements that we need to kind of deal with later on. So this is what we see on the stack. So what we can see now is, so that means destination is really at the location of D plus 1, and source is really at the location of D plus 2. In other words, we know the offset of where we can find destination and where we can find source relative as an offset from where the stack pointer is pointing to. So that's actually what we're going to store as a label. Now I'm going to use my string copy underscore source as a label name, because this way, we can define multiple functions and we won't have a problem with naming these labels because they are prefixed by the function name itself. So this is going to be 2. And then we have my string copy underscore destination as 1. So what I'm trying to do here is I'm trying to use labels to remember the offset to each parameter relative to where the stack pointer points to at the entry point of the subroutine. Yes, that was a long sentence, and every single part of that sentence is important. I already made it as short and concise as possible. Alright, so this may be a good timestamp that you might want to write down, just in case you need to go back and revisit what I just said. Alright, so why do we want to do this, right? Well, we're doing this because now I don't have to use or waste my mental juice to remember where things are, because now they're symbolic. There's a symbolic name to all of this stuff now. So this time, now we can go into here, and the first thing we need to do is to copy whatever source is pointing to whatever destination is pointing to. That's the first thing we need to do. We test whether that is 0 or not later, okay? Because the first operation is to perform the actual copying, which means we need to get the source first. So I'll give you the code to do this, and then I'll explain it, okay? So we'll do a LDI. We can use A, B, or C at this point, okay? So all the registers except for the stack pointer are available for you to use until you get to the return value part. And we are quite a long way from that point, so we can use register A if we want to. So we're going to use LDIA with my string copy source. And what that's going to do is register A is now an offset to where we find source. So it's not even an address at this point. It is simply an offset from where the stack pointer is pointing to in order for me to find source as a parameter. So it's not going to be useful to me until I add the stack pointer to register A. So at this point, A becomes the address of source, which is my parameter. Okay, so we are getting closer to source, but right now we're holding on to not even the parameter itself. We're holding on to the address of the parameter. So we need to dereference it so that we can actually get to the parameter itself. So now we have LDAA. So now A becomes the source, which is basically the value of the parameter source. And even that is not what we want, because we want to get to what it points to. So we need to dereference it yet one more time. And now register A has whatever the parameter source is pointing to. So I know it sounds like a lot. Each step, the concept itself is not important. You just have to track all of these things, carefully. And I would suggest that you comment like what I do here, every single line, make it very clear that you know what is in the register after the operation. So I'm going to pause here to see if you guys have any questions, because this is a little bit of, we have not introduced any new mnemonic or new instruction at this point. We are basically done with all the instructions. But what we have done here is to combine these instructions in order to do what a C program would need to do. All right, so every time I attend a lecture, I'm so glad we have something better to program in than assembly. I have to laugh because I once wrote a real-time kernel. A real-time kernel is kind of like a very tiny little operating system. It doesn't have a file system. It is multi-threading. Has priority queues. It can handle synchronization of threads and so on and so forth. But the entire thing was written in assembly language, because you really cannot write that portion of any operating system in C or C++. So deep within Windows NT, deep within Linux, deep within Mac OS X, which is basically Unix, is a very core portion that cannot be written in C or C++. And that portion has to be written in, guess what? Assembly language. Yeah, so, knowing how and being proficient at programming in assembly language does open up some interesting possibilities when it comes to occupation. All right, so now that we have the right hand side of the assignment operation, in other words, right now we have whatever source is pointing to, we need to copy that to whatever destination is pointing to. Obviously, register A cannot be used anymore because register A now hosts the right hand side of the assignment, so we kind of need to retain that. We could push it on the stack so that we can reuse register A. We could do that, but since we have B and C available, we're going to use register B or C for this purpose, right? So we're going to use an LDI B with my string copy destination this time. Add BD, and then LDBB. So yes, I just broke my own rule because I want you guys to fill in the blanks. Okay, so at this point, register A has the parameter destination, which is not what it points to. So now is a critical moment, because what we have now is register A is the right hand side, which is the value that needs to be copied, and then register B has the address of the left hand side, which is where we want to copy it to. So the next operation is not going to be another LD instruction, because LD is just reading. So given that as a statement, as a hint, what do you think we need to do at this point? Not CPR, because we are not interested in copying to a register, but I think you got the right direction of the concept, but just not taking into consideration that we want to copy into a RAM location. We are not trying to overwrite a register. We're trying to overwrite what a register is pointing to. So What instruction would do that? It's kind of the counterpart of LD. LD reads one location. No, it's the counterpart of LD, which means, so instead of reading a location in RAM, we're trying to overwrite a location in RAM. There's only one instruction that can overwrite locations in RAM, and that is correct. ST, store. Very good. Okay, so ST, and where are we going to store it to? Okay, so which register contains the address of where we need to store to? Oh, I just messed up my comment here. Excuse me. There we go. So let me ask the question again. Which register has the address of where we need to store to? Yep, that's right. Register B, right? I like SpongeBob. Alright, so we are storing to where register B is pointing to, but what value are we going to store at that location? In other words, which register is providing the value that I'm going to use to overwrite the location that register B is pointing to? Register A, very good. Alright, so at this point, we have just accomplished this. Okay, so at this point, we have just accomplished that. So, so I cannot remember who said that earlier. Omer said that. So yes, so in assembly language, what seems like super duper easy in C, in assembly language, it's like, wow, there's a whole bunch of stuff going on behind the scene. Yes, indeed. Alright, so now we have just accomplished the assignment itself, but we have to turn the assignment into a Boolean value because that's what we are supposed to find on the left hand side of the question mark in the ternary expression. So you can see that this is doesn't seem like a comparison, but it is, because what it is trying to do is to determine, is the value that we just copied a 0 or not? Okay, because that's, if you don't see a comparison, it means we're implicitly comparing to 0 and see if it is different from 0. So for those of you who remember, this is the shortcut, right? This is how we say, oh, if you just need to know whether something in a register is 0 or not, we don't have to use a bunch of instructions, load a constant of 0 into another register, and then do a CMP. We just need to do an AND AA, because that forces the value of register A through the ALU and touch the Z and also the S flag. Now the S flag in this case is not useful to us. We can totally ignore that, but we need to use the Z flag. So now we say, okay, JZI to someplace, right? JZI to wherever we need to go in case the value that we just copied turned out to be 0. Okay, so if we need to go to the else portion of this ternary expression. So we're gonna specify a label. So I'm prefixing all my label with the name of the function. So this way there's no way I can have a label name collision between functions, even though I don't have another function in this case. So nonetheless, okay, this is a good practice, okay, just to make sure that our labels are unique. So this is just gonna go to a label called my string copy else, and we'll just stash it here right there. Okay. And we also kind of know that we have to jump around it. Okay, JMPI to my string copy and if, which is going to be the code to return. So that's going to be right here. My string copy, cannot spell, copy and if. There we go. Okay. So are we doing okay so far with the control structure? Because this is basically the same thing as an if then else, right? Because this is the condition of the if, this is how we get to the else branch, and this is whatever follows is corresponding to the then branch here. Are we doing okay so far? Actually, I take it back. Sorry about that. This is our then branch, because the then branch is between the branch to the else branch and the unconditional branch to go around the else branch. So are we doing okay so far with this code? in terms of the control structure. In other words, we are now trying to implement the control structure corresponding to the ternary expression, because we are looking at this as a condition, we are looking at this as our then branch, and we are looking at this as our else branch. Are we good so far? Do we have any questions? I'm just looking at the time here. We may be slightly pushing it. So far, so good. Okay, excellent. All right, so let's deal with the then branch first, okay? Because that's the complicated one, right? Or so it seems. So what we need to do now is to get back to source, plus add 1 to it, and then push it on the stack. Get to destination, add 1 to it, push it on the stack, and then call the subroutine itself. All right, so let's do all that, okay? So LDIA with my string copy source, right? Because we have to deal with source plus 1 first. Add AD LDAA, and that's all we need to do, because this time we don't need to dereference. We just need to get to source, but we do have to remember to increment it by 1, because the value we are pushing on the stack is not source, but source plus 1. So now we can stash it on the stack, which is decrement D STDA. And then after that, we have to push destination plus 1, which is kind of the same code. So it is, this time I can reuse register A, because it's no longer useful to me at this point. So this is my destination. But this time we have to use destination 1 plus, because we have one additional thing on the stack already. So the offset that I have defined the label to is no longer entirely accurate, because I just pushed one additional thing on the stack, which changes the relative position between the destination and where the stack pointer is pointing to, corresponding to the instruction on line 34. That's why we need to add 1 to it. But once we have done this, the rest is kind of the same deal. So I would advise you guys to, kind of comment every single line of this program, so you know what is in the register and why we are decrementing the stack pointer and what we are actually storing onto the stack, with all of these instructions here. So let me just kind of do a quick glance to make sure that this looks right. Yeah, it looks right to me. Oh, I forgot one thing, right? Forgot to increment A, because we are supposed to push destination plus 1. So this increment of A is for pushing 1 plus destination. This 1 plus here is for finding the destination, because we got 1 extra byte on the stack already. All right, so now that we have pushed the 2 arguments, it's time to call the subroutine, which is the same deal. So we have LDIA.6 plus. Decrement D to allocate the space, STDA storing the return address on the stack. Let's see, and then that's all we need to do. Now we can JMPI to the subroutine, which is my string copy, strcpy. And after it returns, we got 2 things that we need to do right away, which is increment D and increment D. This will deallocate the 2 arguments that were pushed on the stack. But more importantly, right now, we have register A containing the return value from the call to my string copy. So at this point, I'm going to split the screen, because I need to show you the C code that we're trying to implement. So this way, on line 15, we are now done with the recursive call to my string copy. So let me ask you this question. This is why I want to do a recursive subroutine. Is this call to my string copy any different from the call to my string copy from main, in terms of how we set up the parameters, how we continue execution at the subroutine, how we clean up the arguments? Is there anything different when we are performing a call from inside the subroutine, the function itself, versus from outside of the function? So I'll let you guys try to answer the question as I continue with the program. The answer is no, absolutely. Okay, so So after all that build up, people are thinking, oh, recursion has to be something special. The answer is no, it is not special at all. Okay, if you are calling a subroutine, whether you're calling from inside the subroutine that you are in or outside, does not make a difference. Okay, so the agreement between the caller and the callee stays exactly the same, even if the caller and the callee are exactly the same subroutine. So I want you guys to keep that in mind, because that will help you in your other classes. In your CISP430 class, when you need to deal with recursive, subroutines and recursive algorithms, I think this will help you. All right, so that is that, and then we just have else to deal with now. So else is really just returning destination itself. I could do something a little bit tricky and save myself some time, which is when we computed the destination earlier, which is right here, we can save a copy to register C. So now, in addition to B being destination, C is also destination. Now, since C is not used by anyone else and there's no function call to anyone up to this point, because remember, this is the else branch. So if you're getting to the else branch, it means you're not performing the recursive call. And if you're not performing the recursive call, then all the registers are still retaining whatever they had earlier. So at this point, I can just say, oh, okay, register C still has whatever we need, which is the destination as a parameter itself. So all we need is a CPR A C, and now register A has the right value to return. So now we get to this point here, and the whole thing should be done. All right, so I think this program is ready to be tested. So here's the last question. How do we confirm this program? How do we know whether this program is working or not? Well, we are supposed to find the ASCII code of THIS at the beginning of buffer, right? So we are supposed to go to location 224 and find the ASCII code of uppercase T, and then the lowercase h, and then lowercase I, and then lowercase s, and then a null terminator after that point. Okay, so that's what we're expecting to see when this program runs. Okay, let's double check and make sure that is the case. So I'm going to test run the program now. I'm already in River Spider, so I just have to say submit temp string copy .ttp asm. Oh, it did not assemble. Okay, let's see what kind of programming poo-poo did I make. Let's see. There we go. String copy and if. Oh, I forgot the underscore. Okay, fine. Alrighty. So what was it again? My string copy and if without the underscore. Okay, there we go. Found it. Put in the underscore. Try to do it one more time. Object code is good. All right. So now we can go back to the analysis tab, right? Because we should be able to see each character being copied starting at location 224, and location 224 in hexadecimal is easy to figure out because it is 256 minus 20, so it should be, let's see, FE, so it should be D0. Okay, so let's find out whether analysis has a write at location D0. All right, so, and we can, no, it's not D0, is it? 224 in hexadecimal. No, we should have reserved. Let me double check. I'm just double checking how many bytes we actually reserved on the stack. It should be 32. All right. Oh, okay. That's a quick and easy way to find it. All right. So if you just look at the beginning of the program, you can see that it is actually E0. This is at location 32, which is in hexadecimal. That is right after we subtract 32 from the stack pointer, which was 0. So location E0 is the first location for the buffer. So that means eventually we should see uppercase T being copied to location E0. So column C should be able to find it. So once I highlight column C, I can type Control G to find a specific pattern. So in this case, I'm trying to locate E0 equals 2, and it cannot find it. Huh. All right. So did I must have messed up the program. This is not good. It's overwriting location 1. That cannot be good because location 1 is part of the program space. So I know I'm running out of time, but this is good in a way. First of all, you guys will know that not everybody can write programs right the first time, especially me. However, the question is, can I find the bug, right? Why am I overwriting location 1? So if I go back here, I can see how register B is 0, 1, and we can see how it went from DE to 0, 1. It's not supposed to be 0, 1. It's supposed to go to location, what did I say again? E0, okay? And the address of the opcode that was incorrect is I think I know why, because we have one too many dereferencing. So it's dereferencing the location of DE. Whatever it is, it's around location 0D. So let's go to location 0D and find out who is there. Okay, so location 0D is LDBB. Alright, so we have destination putting into B, we have add DB, and then we have LDBB. Alright, so let's check whether at location 0A we actually put a 0, 1 into register B. So we did put 0, 1 into register B, and then we add the stack pointer to it, so it becomes DE. DE is the destination. So we get to destination, and then it pulled a byte of 0, 1 locations. That is odd. So that means we pushed the wrong thing on the stack. Because okay, so now we can see what we pushed on the stack when we overwrote location DE. So we did push 0, 1 onto the stack, which means main actually pushed the wrong item on the stack. Alright, so we need to look back into the code, find out why main is pushing the wrong destination on the stack. So we know the problem is in main now. And it is pushing this first. So that part is right. It did push this on the stack. And then when we try to push the buffer on the stack, it is the wrong thing. And that's because we forgot that buffer is on the stack and we're supposed to add the stack pointer to register A in order to become the address of buffer. So let me explain this. This is really important because I stepped on this, obviously. So on line 66, what is being loaded into register A is an offset. It is the offset of where we can find buffer as a local variable from where the stack pointer is pointing to. So without line 67, which I just added, I would have just pushed the offset itself on the stack, which is not very exciting. So that is why it is important to use a add 80. We are basically adding the offset with the stack pointer. So once we have the add 80, we will be finding we'll be pushing the address of the buffer onto the stack. So that is the reason why the program did not work. Okay. So I think this part is really important, as much as you guys would say, but Tech, you just try to save face. No, I'm not trying to save face. I'm telling you that I made a mistake. Okay, so this has nothing to do with your face at all. This has to do with when your program doesn't work. How do you go about debugging your program? What tools are available to you, and what process are you going to use to find out where did my program go wrong? So, and I think that's really important. Debugging is one of those things that I wish most professors would have taught in CISP300 and also 360. But from what I gather from students over many semesters, most professors do not teach how to debug a program. All right, so now it looks a lot better, right? Because we did push E0 on the stack. This is from main. So when we get into the subroutine, E0 gets 5-4, which I think is the uppercase T. And then we can look up what is E1. That should be getting lowercase h. Oops. E1 equals 2. And there are the next one. Yeah, that looks like a lowercase character to me, 6-8. And if we go to location E2, it's getting 6-9. Okay, so we kind of know that it's doing it correctly because 6-8 is lowercase h, and then 6-9 is lowercase I, and then E3 should be getting lowercase s. So that does look like lowercase s because it is after lowercase I. And we need to check one more, right? Because the null character, the null terminator, should be at location E4. So we should see an overwrite at location E4. And that is actually what happened. Cool. Okay, so the program seems to work, seems to be doing what it's supposed to. But one last thing is to make sure that the stack pointer is balanced. In other words, by the time we get to the halt instruction, we want to make sure that register D is going back to 0. And that it did. Okay, so the program does seem to be working correctly. And we also want to make sure that register A is the return value, which is where we're supposed to find destination. And that is also the case, because we can see how register A has the address of buffer, which is E0 here. That is the return value from the last return of the recursive call. All right, so I know this is a lot to take in, but this program, if you have not done it already, go make a copy of this assembler right now, okay? Because the trace is how you can actually visualize, you can actually see how recursion takes place, how it's using up more and more locations on the stack. You can even see what it is storing on the stack. Oh, this is storing the argument, this is storing another argument, this is storing the return address, and so on. So by looking at the trace really kind of line by line and mapping column A to the address in the assemble tab, now you have a complete picture of what is happening when a program like this is executing. So this is giving you a X-ray vision basically of recursive function calls. And once you understand everything is really on the stack, that means your local variables, your parameters, your return address, they're all on the stack. That really should help you in time to demystify the concept of recursion, because recursion is nothing special. It does the same type of thing as calling a function from any place. It's not special in any way. It's the only part that is special about recursive function call is how we write the code to begin with. But in this class, I always give you the C code. So your job is not to come up with the C code, which is the difficult part of coming up with a recursive algorithm. Your job is to translate the C code into assembly language, and that is not going to be nearly as complicated as coming up with the recursive code to begin with. All right, so the lecture is over, and I am over by like 15 minutes. I'll give that time back to you for tonight's lab. So let me show you tonight's lab first. And because this is one of the first actual program that you need to do for this class in TTPSM. This isn't going to be a complete program. Let's see, which one are we going to be doing today? I think we're supposed to be doing the function call. Let me check this one. Yep, that's the one. All right. All right. So there are two parts to this. I'll give you the first part first. So the first part you do have to finish by tonight. So I'm going to give you guys until 10:05 p.m. So that way you have time, and I'll give you the answer at 10:05 p.m. There is a passcode. The passcode or the access code is swap because that's the name of the subroutine that you need to implement. There we go. And then save and release, save and publish. There we go. All right, so there are two parts to it. The first part is really kind of the same as the usual lab. Some multiple choice questions. Some questions that requires a numerical answer. The second part is going to be a program that you have to turn in, and that is not due tonight. Okay, I know it is not realistic for you guys to be able to finish the program by tonight. So that is why we have an extra assignment to capture the program that you're going to write, which is this one here. You cannot see it yet because I haven't released it. So let me go ahead and release it now. So this one is a regular program, a regular assignment, and you have to turn in the TTP-ASM code for this assignment. So for this one, you do have, I'll give you guys a week to do this. So it's going to do, let's see, today. Okay, we are crossing months, and that means next Tuesday is the 3rd, May 3rd. There we go. So May 3rd, and it's going to do at the beginning of the class, so it's going to be 5:30 p.m. May 3rd, 5:30 p.m. There we go. Save and publish. There we go. All right, so let me go back to kind of mention what you need to do, what you need to turn in at what time. There we go. All right, so what you need to finish by tonight is this one, which is just a function called lab. This is the part where you need to kind of understand the concepts, answer a few multiple choice questions, answer a few numerical answers. So that one should not take too much time. You should be able to get it done by 10:05 tonight. The second part, which is the actual program that you have to write, that might take you some time. Okay, it might take you some time to write, take some time to debug and test your program. That one is due in a week, which means you have, I wouldn't say plenty of time. I would get on it as soon as possible, because starting on this program next Monday, at night is probably not a good idea. Okay, so I would suggest getting started with this one as early as possible. So those are the two parts of the activities that you have to do. Do we have any questions before I kind of let you guys loose to get on with the lab. All right, there are no questions. Oh, okay, there we go. Mark has a question. Go ahead. And by the way, the assembler still has the code for my string copy. So once again, if you have not done so already, go make a copy for yourself. Will there be some sort of program or something to check our program is functional, or is the analysis tab the best way to do it? It's supposed to. Okay, so the first thing, so that's a very good question, Mark. You want to run the C code first because it gives you the C code as well. So you want to run the C code, and then you want to know how do you debug the C code, right? How do you know the effect of the program in C code? So once you understand that part, then you can basically translate that to how you can test the assembly code. Okay, let me address that a little bit more before I get off the channel. Okay, so let me get back to function calls, and I'm gonna look at preview. Okay, so as a part of the quiz, you are presented with the C code, and I cannot remember which question has the C code. I'm gonna guess question 9 because I saw the reference to. Oh, okay. Maybe 8? Nope. Will there be a separate lab due on Thursday? I haven't decided yet. But for now, let me see if I can find the C code first, because I want to address Mark's question of how to test. How do we know this program works or not? Question 4. Thank you. That's my next link. There we go. All right. So question 4 is giving you the template. It's giving you the C code entirely. This is the entire C code. You do need to do a pound include standard integer in order for this program to work. But the way you debug this program, or the way you confirm whether this program is working or not, is you should be able to see the values of x and y in main being exchanged. So x started with a value of 3, y started with a value of 7. When the program is done, you should see those two exchanged. In other words, x should end up with a value of 7, and then y should end up with a value of 3. So let me just do this because since Mark just asked the question. So I'm going to use onlinegdb.com because that's kind of the quick and dirty way to run the program. So we'll go ahead and copy and paste this code in. Okay, too much. Give me a second here. Alright, it's almost there. Alright, so copy and paste. There we go. And remember, you need the pound include here. So pound include standard integer.h. Alright, so now this program should compile and it should run. So we'll specify this is a C program and put a breakpoint on line 15 right before the call, and put a breakpoint on line 16 right after the call. So let's go ahead and debug. Alright, so there we go. And we should be at a breakpoint at this point. Info break. Alright, so it's not at a breakpoint because I haven't run the program yet. So we'll go ahead and run the program. And this is right before we get into the subroutine swap, and we can see how variable x has a value of 3, variable y has a value of 7. So if I were to continue execution to the next breakpoint, in GDB it's C for continue. There we go. So at this point, you can see the two variables have their values exchanged. X now has a value of 7, Y now has a value of 3. So that is supposed to be the end effect of the code that is written in C. So your assembly language implementation of swap should accomplish the same as what is specified in the C code here. It's not just that we have to exchange the two variables in main, it is to exchange whatever PTR1 is pointing to with whatever PTR2 is pointing to. So, I have had people in the past, who turn in code to specifically exchange the content, the location of wherever X is and wherever Y is. Yeah, I didn't count that as a correct implementation because that is not implementing the actual logic in the swap function. So your job is really to implement the content of the swap function here. So does that answer your question? I mean, if Mark is still listening. All right. Yeah, sure. So the first thing you need to do, because that is how you're going to debug your program. So the first thing you need to do is to find out what location in text toy processor is corresponding to X and which location is corresponding to Y. Because without knowing those two locations, you wouldn't be able to check and compare to make sure that the content at those two locations were in fact exchanged by your function. So that would be the first thing you need to do, which is basically to understand how the stack is being utilized to store the local variables, to store the arguments, and also the return address, blah 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 blah. That is kind of the purpose of this homework assignment, is to get you guys to actually write some code so that you understand all of the stuff better, all the stuff that we talked about today. All right, so any other questions before I let you guys go? Okay, I'm just checking the text channel to make sure I didn't miss anything. All right. Oh, camera is blocking the value. Sorry about that. So if I can just turn it off. Give me a second. There we go. Oh. Nope. There we go. Okay. All right. It's still streaming, so you just have to wait a little bit to get to that. All right. So looks like we are good here. I'm going to stop streaming and screen share, and then I'll be back in about 5 minutes to see if I have any questions to answer.